Okay, differentials and change. So what does this have to do with anything? Well, um, Calc 3 is an extension of Calc 1, but we're doing Calc 1 in 3D. So differentials is something that you studied in Calc 1. So let's do a quick review of that, and then we'll do the Calc 3 version. All right, here we go. So review from Math 250. That's Calc 1. So what about it? Well, when you studied differentials back in Calc 1, and you may have forgotten, so this is just a little refresher for you, the differential of a function y equals f of x is f prime of x multiplied with dx. And usually they denote it with dy. So in other words, they'll go like this: dy equals f prime of x dx. And this is known as the differential. Now, what is it used for? It's used to approximate changes in the function y. And you can compare it to the actual change in y, which is the difference between the y coordinates of the 2 points. And usually it's denoted delta y. So delta y is the difference of the y coordinates of 2 points. Now, if the function is differentiable at this point, say x equals a, then they call this the linear approximation of y equals f of x at that point x equals a, is L of x, L stands for linear, of x is equal to f of a plus f prime of a multiplied by the quantity x minus a. Now, where the heck did this come from? So before we do an example from Calc 1, I just want to let you know this is in fact the equation of the tangent line to the graph of y equals f of x at the point when x is equal to a. Really? Well, it doesn't look like it. It looks kind of funky. Yeah, well, if I gave you, let's just talk about the point A, f of a, let's say is on a graph, like, here's a graph. Let's say right there is the point A, f of a. And I draw a tangent line to that point, like so. Well, the slope of this tangent line, I hope you would agree, is the derivative f prime evaluated at a, right? And then if I use the equation for a line known as the point slope form, then the point slope form would be y minus the y coordinate of the point, f of a, equals m, the slope, f prime of a, multiplied by the quantity x minus a. Yeah, so what? Well, if I solve this equation for y, just by adding f of a to both sides of the equation, boom, there I have it. This is the same as this. So what do I use it for? Well, because this tangent line, if I get in a really close interval of a, if I just stick to this little interval, it can almost look like the graph of the function itself. I know it's a straight line and the graph is curvy, but if I stay in a really close neighborhood here of a and just pick little points that are close to a, I can use this tangent line equation as a good approximation for the actual function itself. Now, obviously, if I pick a point way the heck over here that's super far away from that area, then this equation for the tangent line is a poor approximation of the function. But if I stay pretty close, I'm good. So let's do an example from Calc 1. And this is actually a problem I gave on a quiz to my Calc 1 students. Okay, so there you go. So here's a function y equals f of x, which is x squared, and you guys know that's a parabola, right? And if we talk about the point when x is equal to 1, this point right here, 1, 1, if I draw a tangent line to it, as long as I stay really close to the 1, in an interval that's about the 1, this tangent line kind of looks like almost the same as the graph. It's not exactly straight, but okay. So let's find the differential of y when x goes from 1 to 1.01. So now they're asking me to approximate a change. So dy is f prime of x dx. That's the differential. And for us, f prime is, well, what's the derivative of x squared?
2x.
So this is 2x. And so there's your differential. That is known as the differential of y, okay? And we're going to use it to approximate changes in the y coordinate. That's what they use differentials for. So if we're going to use it to approximate the change as x goes from 1 to 1.01, delta x, or the change of x, is basically the same as the dx here. So for us, the dx is 1.01 minus 1, which is simply 0.01. So that's the change in x. And then x, which x should we use? The starting point 1 or the 1.01? What do you guys think? Do you remember this from Calc 1 at all?
The starting point.
Yes, the starting point. So x gets substituted with a 1. And then we actually multiply this together. 2 times 1 times 0.01. The change in y, so this is approximating the change in y, is 0.02. And we're done with letter A. It's approximating the change in the y coordinate as the point goes from 1 to 1.01. Now, is it a good approximation? Well, let's find out. Let's find the linear approximation function of y equals f of x at x equals 1. That's just a fancy schmancy way of saying, go get me the tangent line equation, okay? Because that's the linear approximating function. So we know the slope, which if you want, you can call it m, is f prime of 1. So if f prime is 2x, we'll have 2 times 1, which is 2. And we know the x coordinate of the point is 1. So the y coordinate will be f evaluated at 1, which is 1 squared, which is 1. So now when we use this point slope form for the equation of a line, we get this. And then if I rearrange it by adding 1 to both sides of the equation, there is my linear approximating function. And the book calls this L of x. But it's just your tangent line, that's all. Okay, so we did that. We found the linear approximation function. Now what? We're going to use it to approximate f evaluated at 1.01. So the linear approximating function evaluated at the 1.01 is 1 plus 2 times 1.01 minus 1, and then you get 1 plus 2 times 0.01, and I get 1.02. Okay, now is that a good approximation? What's the actual f of 1.01? Well, f of x is equal to x squared. We know that. So what is f evaluated at 1.01? Well, whip out the calculator. What's 1.01 squared? I get 1.0201. So that's the actual f evaluated at 1.01. So now what I'd like you to do is I'd like you to compare these two values. Are they pretty good? Are they pretty close? Using the tangent line, is that a pretty good approximation of the actual function? Not bad, huh? I forgot to do the actual change up here. I forgot, sorry. The actual change of y, sorry about that, which is f evaluated at x plus delta x minus f of x. Sorry, I forgot that last part. So this is 1.01 squared minus 1 squared. And so if I do that, I get 1.0201 minus 1, which is 0.0201. So this is the actual change in the y coordinates. So now compare these two values, the differential, which is basically used to approximate changes in the y-coordinate, compare it to the actual change in the y-coordinate. It's a pretty good approximation. Wouldn't you agree?
Yes.
And then down here, these two are pretty close. So I would say that tangent line is a pretty good approximation for the function evaluated. Now, again, you don't want to use your approximating function for points that are far away from the point where the tangent line was found. Otherwise, it may not be so good. Okay. So I'm going to just say pretty good approximation here. And now let's get back to Math 252. Okay, what does this have to do with Calculus 3? Well, let's do the definition for the total differential for a function of two variables here in Calc 3. So let's say you had z equals fxy, and let's say delta x and delta y are increments of x and y. Then the differentials of the independent variables of x and y are dx, which is, we'll just say is pretty much the same as delta x, and dy will be the same as delta y. Then the total differential of the dependent variable z is given by the partial of z with respect to x times the change of x plus the partial of z with respect to y times the change in y. And there you go. Now, what do you use this for? You use this differential to approximate changes in the z coordinate. You know, the altitude changes. So if you were going to compare it to actual change, your delta z actual change is f evaluated at x plus delta x, y plus delta y, minus, so you evaluate it at this point, minus the function evaluated at the original point. And usually dz and delta z are pretty good. They're pretty close because the dz, the total differential, is a good approximation. Okay, now what about the linear approximation function for a function of two variables? Aha! It's the same as the tangent plane equation. They just rearranged it and solved it for z. I'm not kidding you, people. So if you'll recall, if you have a function z equals f of xy, so from last time, if I rearrange it and get everything on one side and 0 on the other, this is now called big F, which is a function of three variables. The gradient of big F, which is a vector, fx, fy, fz, which is going to be whatever little fx is, because the only x's and y's are in little fy, and -1 for this function of two variables. And then when I use this as the normal vector to the tangent plane, these are the same. This is the normal vector to the tangent plane, to the surface given by z equals fxy. And if you'll recall, to get the equation of a tangent plane, you take your normal vector components. If this is the equation in standard form, x minus, let's say you do it as a point to the point x1, y1, z1, say, and they're using a, b, and f of a, b. So I guess I should use that as the coordinates. You're going to do this, and then your -1, and then you'll have z minus f of ab equals 0. And then when you rearrange this and you solve it for z, you'll basically get that. So it's just the same as the equation for the tangent plane. And you can use the tangent plane as a pretty good approximation of your surface. So just visually speaking, let's say you had some, let's say, capping surface here given by a function of two variables like this. And let's say you picked a point right there and you figured out the tangent plane to that point. So there's the point right there, and you've got some tangent plane right there. If you stay in a close vicinity of this point down here, AB, you know, maybe within a little delta neighborhood, then any points that you pick down here in the XY plane that are on the surface, if you use the tangent plane instead as your equation, it's a pretty good approximation of the surface. You know, yes, I mean, if you did a close-up shot, yeah, the surface is curvy and the tangent plane is flat, but as long as you stay really close to the point in question, it's pretty good approximation. Okay, so let's just do some examples. We'll prove it. So here's a surface, 12 minus 4x squared minus 8y squared. I think that's a paraboloid that would look something like this. Okay, and we're going to find the linear approximating function at the point negative 1, 4. Okay, fine. That's basically saying find the tangent plane to the surface at the point when x and y are negative 1 and 4 respectively. Okay, now the question is, what's the z coordinate at that point? So let's go get that now. So the z coordinate would be f evaluated at negative 1, 4. So you'd have to go 12 minus 4 times negative 1 squared minus 8 times 4 squared, and then get all that stuff and punch it up into the calculator. I get, negative 120. Okay, so the point on this paraboloid would be negative 1, 4, negative 120. So actually, it would probably be way down here. Because we have a negative z coordinate. Go get the tangent plane at that point. Fine. So you're going to go, this is how I roll. I get everything on one side and 0 on the other. And your Briggs book is going to do this in a different way. But I really wish you'd do it my way because it'll help you for later. All right, so I get everything on one side and 0 on the other. And there's my big F, which is a function of 3 variables. So my gradient, del F, which consists of the partials, for me is going to be negative 8x, negative 16y, negative 1. And when I evaluate it at the point negative 1, 4, negative 120, I get negative 8 times negative 1 for the first component, negative 16 times 4 for the second component, and negative 1 for the last component. So this is going to be the normal vector to the tangent plane. Right there. That's the normal vector to the tangent plane. So this is a picture of the tangent plane. This is the normal vector. And so you're going to use it to go get your tangent plane equation. Great. So 8 times the quantity x minus the x coordinate of the point. So x minus a minus 1. And then we have the minus 64, y minus 4. Then we have the minus 1, z minus a negative 120 equals 0. That's standard form. That's the standard form for our tangent plane. And the book gives you like this quick and dirty way to find it. I never use it. I'm going to multiply out and solve this for z. And so when I solve it for z, which they call big L of xy, that's the linear approximating function, which is a function of 2 variables. And I make it look a little prettier by collecting my like terms. I get z is equal to 8x minus 64y plus 144. La, 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 la. There it is. There is my linear approximating function, which is the same as the tangent plane. People, it's the same. Don't be confused.
Professor, I have a question.
Sure.
When you got everything to one side in the homework, it was moving, instead of moving z, it was moving everything else. And so it was changing the signs of the point when you plugged in negative 1, 4.
Hang on a minute there, Hannah. When I moved everything to one side and I got 0 on the other, I wasn't solving for z there, was I? I was just moving everything to one side and getting 0 on the other.
Yeah.
That's a different deal. That is because you want to get the general representation for a surface. But now what we're doing is a very different thing. We're trying to find the linear approximating function. And I get that you're saying, well, how come you wanted me to get everything on one side and 0 on the other for that, but not for this? Just because the book likes you to have it written as an explicit function of X and Y.
There was just like one problem where instead of -1, we got +1 for the Z.
Okay, well, that might have been, Hannah, because they got everything on the other side. Can you hear me okay?
Yeah, I can hear you.
Okay, so what I'm saying, Hannah, is remember I told you when you get everything on one side and 0 on the other, it doesn't matter which side, just so long as you get everything on one side and 0 on the other? Do you remember me saying that at all?
Yeah.
Good. So if I got everything on the other side, Hannah, where I would subtract 12 and add 4x squared y to both sides and add 8y squared to both sides, and then I called this mess on the left-hand side big F of x, y, z, would it still work? Yes. Well, how come? Well, your gradient is going to have all opposite in signs, right? Where you're going to have your first partial with respect to x will be a positive 8x. Do you see why?
Mm-hmm. Mm-hmm.
And then your first partial of f with respect to y would be a positive 16y. And then what would your first partial of f with respect to z be?
+1.
And would that work? Sure, Hannah, because remember that we're finding a normal vector to the tangent plane. So the version where you'd have a +1 instead of a -1, which you're talking about, would be punching out of the tangent plane upward. If you can see my diagram here?
Mm-hmm.
And it's a normal vector to the tangent plane. But you can use the other normal vector that's punching downward or pointing down, which is the one that I'm using with the -1, because that's still a normal vector to the tangent plane.
I used the method that you just did where you got the Z to be a -1,
Okay.
but it was incorrect on the homework because they wanted to move it to the other way.
Well, let's revisit that after class. But I claim that you probably did some other little mistake because we still should end up with the same exact answer.
Okay.
Still have to end up with the same exact answer. You're going to solve it for z, and you'll get z equals the stuff. And that is the equation for the tangent plane. So let's talk about that after class if we have time, or if you can make my office time today, that would be great. Can you?
Yes.
Awesome. I'll look forward to seeing you there, and we'll look at that problem. But I claim this way should work perfectly okay. So let's take a look at using our answer to part A. That would be this tangent plane where the equation's just rearranged. And we're going to evaluate it at -1.05, 3.95. All you're going to do is plug it in. So F evaluated at -1.05, 3.95 would be 8 times -1.05 minus 64 times 3.95. Definitely have a calculator handy. And I get, yikes, negative 117.2. All righty. Now, what's your actual value? Well, what's the function itself evaluated at -1.05, 3.95? And let's just go to the beginning of the problem here. Your paraboloid function equation is z equals fxy 12 minus 4x squared y. So of 12 minus 4 times -1.05 squared. All right, minus 8y squared. So that's 8 times 3.95 squared. And again, whip out the calculator, and I get about -117.2. 0.23. So when you compare these two values, do you think that our linear approximating function is a pretty good approximation? Yes or no?
Yeah.
Yeah, pretty good. Pretty good approximation. I'm thinking, hey, you know, if you're only off by 300ths, can't beat it. Okay, so letter C, we're going to do the differential. And that's real easy because that's just the formula and the theorem. And then we're going to use the differential to approximate changes in the altitude and see if it's real close to the actual changes in the altitude. Okay, so dz from the theorem is the partial of z with respect to x times the change of x, delta x, dx, or delta x, same thing, plus dz dy times dy. That's it. We're done with letter C. Great. Move on. Letter D says use that differential to approximate changes in z when your point xy starts at -1, 4 and moves over to this other point, which is pretty close by, -1.05, 3.95. Okay, so before I start plugging in to my differential, I need to get my dx, which is basically the same as delta x. So that's going to be the ending point, -1.05, minus -1. And so what the heck is that going to be? I think it's going to be a negative, so it's going to be -0.05, like so. And then your change in y, which we use delta y, is going to be what? 3.95 minus 4. And so I think that's going to be also -0.05. Yeah. That doesn't always happen, but okay. So that's what's going to get substituted in for the dx and dy. So before we move on, though, what is dz dx? So dz dx, I think we agreed was what for this problem? Is -8x. And then the dz dy was -16y. So here's our differential in full. And so when we start plugging in the starting point for x is -1, and then our delta x was -0.05 plus -16 times the y, which is 4, and then your change in y. And then I get, this is what I ended up getting. See, I got 2.8. That's the change in altitude. So then if you try to punch, and so it looks like I have a little bit of a typo here. This should be -1.05. So if you evaluate, so let me just see if I had a typo somewhere else here. I'm looking at my notes here because I have a little, yeah, that was 1.05 like we did before. So sorry, this should be a 1.05 right there to match the other one. So the delta z, which is actual change in the altitude, is f evaluated at -1.05, 3.95, minus the function evaluated at -1.4. And so I'm going to go, all right, I got that -117.23 minus, now I didn't evaluate the function at -1.4, but well, I did when I was doing the tangent plane, so I'll plug that in. So -120. Punch this up in the old calculator. I get 2.77. Okay, now is the time to compare. What do you think? This is the change in altitude. I use my differential to get the change in altitude, but that's pretty close to the actual change in altitude. Not a bad approximation. Now, why would you do any of this? Well, sometimes you don't have access to the actual function. You only have access to changes over, say, a period of time. And so you can say, well, the approximation is pretty good. So you're good to go. So when do they use these differentials? Like, who cares? Well, as an engineer, you care. So let me do an actual application of these differentials, so you may have a reason to care. So I don't know if you've ever measured anything with a tape measure or a yardstick or a ruler or whatever, but measuring sticks are not exactly accurate. They're usually off by a little bit because there's nothing perfect in this world. Okay, so let's say your measuring tool, the possible error in measuring your box is plus or minus 0.1 millimeters, just because, you know, you don't have perfection with your tool. And let's say you measure the box, X is 50 centimeters, you know, it could be like a length, say, and then 50 centimeters, and then say the width is 20 centimeters, and let's say your height is 15 centimeters. Now, just using these given measurements, what is the volume of this box? Well, it's 50 times 20 times 15 centimeters cubed. I get 15,000 centimeters cubed is the measured volume of the box, but that's not exact. So it's off somehow because of the propagated error of your measuring tool. So let's compute the differential, and then we'll estimate that propagated error using differentials. So the dV, and by the way, this is not the chain rule because we're not taking the derivative with respect to time, although it may look like it to you. It has a little bit of the flavor, but you're going to take the partial of v with respect to x and multiply it by dx plus dv dy dy plus dv dz dz. And then the dx and the dy and the dz are all the same. That's plus or minus the 0.1 millimeters. Now we want to have our units all be uniform. It looks like that this millimeters doesn't match the centimeters. So let's convert millimeters to centimeters. So 0.1 millimeter is equal to how many centimeters? You guys know how to figure this out? You know, some stoichiometry. I believe that there are 10 millimeters in 1 centimeter. And so if you do this, something like this, you'll get what?
That'd be 0.01 centimeters.
Yeah, so you want everything in the same units, otherwise we'll get in some weird trouble here. So the dx, the dy, and the dz are all going to be 0.0 plus or minus 0.01 centimeters. What about the dv dx? So the differential is going to be, well, when I take the derivative of x, y, z with respect to x, I get y, z, and you're going to multiply that by dx plus the partial with respect to y would be xz and then dy plus the partial with respect to z is xy. And so you use the measured values. You have 20 times 15 if we use the measurements, plus or minus 0.01 plus xy 50 times 15 times plus or minus 0.01 plus 50 times 20 times plus or minus 0.01. I'm going to ignore the plus or minus 0.01 and sort of factor it out, if you will, like so. And then you multiply all these guys together, I get 2050, and that's centimeters squared. And then if you multiply these guys together, I get plus or minus 20.5 centimeters cubed. So that's how far off we are with the calculated volume of the box. That's quite an error. And when you think about it, that's nuts, because here it seemed like your tool being off only plus or minus 0.1 millimeters. Oh man, that's really tiny. It's like a little speck, right? But it does start propagating, and it does impact how far off you are with volume, or if you were calculating surface area. Now, what about the relative error? So relative error is where you basically do a ratio. you compare your delta V, which we're going to use dV because dV is essentially close to delta V, and divide it by V. So we got 20.5, and the units are going to cancel, so I'm just not even putting them in there. And then you divide by the measure volume, 15,000, and I get 0.0014. And when I convert to percent by moving the decimal place over 2 spots, I get 0.14%. So it does seem like the volume is off quite a bit, but relatively speaking, it's only off by a fraction of a percent. So I guess it's not too bad. But that is one of the applications of differentials. And I like to see applications as an engineer, you know, and I'm sure some of you are future engineers. You like to see, like, what does all this stuff have to do with anything? And there you go. And we're officially done with the section 15.6, tangent planes, normal lines, and differentials. Congratulations. Questions? Are you guys still there?
Yeah, I'm still here.
Yeah.
You're still alive? You're still awake?
Still trudging through.
Still trying to get through this. It's not easy. Zooming is not easy. I know.
Yeah.
I was Zooming in a meeting yesterday. It's tough. You know, tough to stay focused because there's lots of distractions, like checking email or whatever. All right, so if nobody has any questions, we're moving on to one of the most fun parts of the entire chapter. I think you're going to love it. Finding maximums and minimums. Do you remember doing that in Calc 1? Sure you do.
No.
Sure you do. You did a lot of that in Calc 1. I'm sure you remember having to find a max or a min. Or
Was that part of like the optimization?
Yeah.
Oh.
We're going to do optimization now. Calc 3 style, baby. And it's great. I think you're going to like it. Most students that I've had in Calc 3 tell me they love this stuff. So I think you will too. So we're going to look at section 15.7, which is going to give us one approach to finding extrema. And then in 15.8, we're going to look at another method that will allow us to find the maxes and mins if you have what's called a constraint. So it's constrained optimization. It's a little different flavor. That's the Lagrange multiplier method. So I think you'll like both. So it's going to challenge you a little bit because you do have to have really good algebra skills. Really? Yeah. You have to be good at solving systems of equations, all kinds of systems of equations. In particular, you might be asked to solve a system of nonlinear equations. So that's a little bit tough. And when you took pre-calc, they did a little bit of it, but not some of the hard ones that we're going to be doing. We're going to be solving nonlinear systems on steroids. Yeah, it's kind of fun, but we'll do examples, so hopefully you'll get through this. All right, let's do a quick review of Math 250 again, and then we'll see how this goes. So recall from Math 250, if you were given, say, the graph of some function here like this, when they asked you to find maximums and minimums, let me do it like this, like that. Let's say if they were asking you to find it on an interval A to B, there were different kinds of maxes and mins. They might talk about a relative or an absolute. So a relative maximum might be that guy right there, the top of a mountain. But if you were given a closed interval, you may be asked to find an absolute max. And since this guy, even though it might not be the top of a mountain, or it might be, that's the absolute max. Now, the absolute min here is the same as the relative min. because it's the smallest y value there on the block, okay? So in this class, I don't have time to do absolute extrema, but it is in my book, so I encourage you to read it. I'm not going to quiz you on it, though, or give you homework. We're just short on time. So we're going to do a relative extrema only. So when you took Calc 1, what was the procedure that you used to get these relative extrema? So let me remind you that you first went and found the derivative, fine. And then the second thing you did is you went to find critical points. And critical points were defined as points where f prime was equal to 0 or where f prime was equal to undefined. Now, just because you got a critical point doesn't mean that, oh, for sure there was a max or a min there. You had to do a little bit of extra work. So may I please remind you that you had to do one of two tests to figure out if you had a max or a min on your hands, or because it could have been what we call an inflection point. You had to do the increasing decreasing test, which you figured out if the slopes were decreasing or and decreasing after, it meant you had a max, or if the slopes were decreasing prior to the critical point but increasing after, you had a min. And if neither of those happened, you had an inflection point, or you had to perform something called the second derivative test, okay, to see if the critical number was an extrema or not. So this was the process, and we're going to have a similar analogous process here in Calc 3. So first, though, let's define what a relative extrema is for us folks here in Calculus 3. So we're going to look at extrema for functions of two variables only, because we want to keep it kind of easy here. So if you had some surface, say like so, given by a function of two variables, z equals fxy, then if you have a relative minimum, that would mean, and you had this, by the way, this x naught, y naught will be a critical point. And this definition doesn't tell you how to find the critical points. We'll get to that in a moment. But if you did have a critical point, then the min would be, well, everybody around that minimum on some little region R down here in the XY plane would, all the Z values would be taller than the Z value of the minimum, because that guy's the shortest guy on the block. On the other hand, if you had a relative maximum, it would mean that that Z coordinate of that critical point would be greater than everybody else in that little open disk, because he's the tallest guy on the block. Fine. And then here's a little picture where you've got maxes and mins. So you can see that all the tops of the peaks there, that would be the relative maximums. And then the valleys would be all of the relative minimums. So this guy has a whole bunch of everything. It's kind of a cool surface. So how do you locate these relative extrema? Well, you got to go get those critical points. So where are they? Well, you're going to figure out where your derivative is 0, in particular where your gradient is the 0 vector. These are called critical points. So let's do the official definition of critical point, and then we'll do some examples. So let's say you have a function f, which is a function of two variables here, and you've got some open region R that's similar to an open interval in Calc 1, containing this point x naught, y naught. This point, x naught, y naught, is considered a critical point if one of the following is true. The first partial of f with respect to x is equal to 0 at that point. And when you evaluate the first partial with respect to y at that point, you also get it equal to 0. So the partials are simultaneously equal to 0. Not one or the other, but both. Now, the other way you can have a critical point is if your first partial evaluated at the point is undefined, or the other partial evaluated at that point is undefined. So the undefined is an either or proposition, which is different from an and. And if you take computer code, you know that an and is definitely different from an or statement. And you need both the operands to be true for the overall statement to be true. And with an or statement, you just need one or the other to be true, or both, in order to be true. So here's a picture. When your gradient, which contains those partials, is the zero vector, you got a critical point. And that means every directional derivative, that's slope, at that point is zero. And I hope you can appreciate when you're at the top of, say, a peak, or at the bottom, you got a valley there. If you were to make a little tangent plane, do you see how the tangent plane is horizontal at either the peak or the valley? And that's key. You're going to have a horizontal tangent plane. Now, what is the equation for a horizontal tangent plane? Well, remember that if you did get everything on one side and zero on the other, like I like you to do, and you've got a function of 3 variables, your normal vector is going to be the gradient of big F. Oops. But if you're, and the gradient of big F, if you have a function of little f, is you'll have this, and this will be either 1 or -1, in this case, -1. But if these two guys are 0, then your normal vector will either be 0, 0, -1, and that means it's pointing down, or strictly pointing down, it's vertically downward, or it would be 0, 0, 1, which would mean it's punching upward. So either way, it's going to be a vertical vector. And then your equation for your tangent plane is simply going to be 1 times z minus some number, that would be the z coordinate at that critical point, equal to 0. So your tangent plane would look like z equals a constant. And that's what planes look like when they're horizontal and they're parallel to the xy plane. Cool beans, baby. Okay, so let's do the theorem that's analogous to the theorem you studied in Calc 1. Believe it or not, you studied a theorem in Calc 1 that said this very same thing. If the function has a relative extremum, that just means max or min, at a critical point on an open region R, then x naught, y naught is a critical point. Now careful, because the reverse is not necessarily true. And this is the same for Calc 1. When I teach Calc 1, I have to remind my students that the reverse of this theorem is not necessarily true. In other words, you can have a critical point in hand, but it may not correspond to a max or a min. Remember, it could be like an inflection point or something like so. So you have to be careful, because the same is true for us. Just because you have a critical point, I got a critical point, yay, hallelujah, great. But it might be a max and it might be a min, but it might be neither. Well, is it an inflection point? Well, we don't really have inflection points in Calc 3. We got something else. And you'll see what that is in the next 5 or 10 minutes. So keep your eyes open and you'll see what it is. You don't call them inflection points in Calc 3. All right, I'm going to do some cheesy, sleazy problems first, and then we'll do an actual problem. I just want to do some prep problems so you see this idea of critical points. And then you're going to try one. Oh yeah, I got one lined up just for you. Fun times. Okay, so the prep quickie problems are, and I say quickie problems because you're never going to do them like I'm doing them. I'm just sort of doing a partial bit of the strategy, just to get you, just to get your taste buds, you know, going, inspired. All right, so here we have some surface given by fxy equals 1 plus x squared plus y squared. Great. Let's find relative extrema sort of the cheesy way. So you first go get your partials, and I get 2x for the partial with respect to x, and I get the partial with respect to y is 2y. Now, when I simultaneously set both of these partials equal to 0, that's how you find critical points. I have a system of equations, but it's kind of like a not even a real fun system of equations because it's like, that's not like exciting. You're just going to have x equals 0 and y equals 0. In other words, the point 0, 0 is a critical point. And we're done. Now, does that correspond to a max or a min? And this is where we're going to do it the cheesy, sleazy way by thinking about the equation. The function looks like 1 plus x squared and y squared. Well, x squared and y squared are always going to be non-negative, right? They're either going to be 0 or something positive. So this critical point most likely is a minimum. It's the lowest that the function can ever get. And that's true because it turns out when you graph this surface, it's an upward facing paraboloid where the vertex is located there at the point 0, 0, 1. So this critical point does in fact correspond to a minimum. In fact, it's the absolute minimum. Not just a relative minimum, it's an absolute minimum. Great. So that's a critical point, and it did correspond to an extrema. Okay, easy, cheesy problem. Let's do another little cheesy problem here. fxy equals 1 minus the quantity x squared plus y squared to the 1/3 power. Okay, I'm going to use the chain rule here real quick to get these partials. Let's see, negative 1/3 the quantity x squared plus y squared to the 1/3 minus 1 is negative 2/3 times the derivative of x squared plus y squared with respect to x. When I rewrite this in terms of positive exponents, I get this. Okay, and I'll do the same thing to get the partial with respect to y. I end up getting negative 1/3 the quantity x squared plus y squared raised to the negative 2/3 power times 2y. I'll rewrite that with positive exponents also. Now, the system of equations, when we set both of these partials equal to 0, oh my gosh, that's kind of a hot mess. Well, how do you know when a function that looks like a quotient is equal to 0? Isn't it when the numerator is equal to 0? Yes. So when negative 2x equals 0, well, that's when x equals 0. And when we do the same thing for the other partial, setting its numerator equal to 0, I get negative 2y equals 0. So, oh, wait a minute, I get 0, 0 being a critical point again. But wait a minute, I claim not only does it make those numerators equal to 0, it's also going to make the denominators equal to 0. So it's really, this critical point is where fx and fy are undefined. They aren't really equal to 0. fx and fy are undefined. And remember, that is one way you could have a critical point where your partials are undefined. So what? Well, is this a max or a min, or what is it? If you graph this surface, it's kind of a cool looking surface. It kind of looks like one of those Hershey Kiss candies. I don't know if you guys are into chocolate candies. And so the critical point when the point 0, 0 occurs, and that's at the point 0, 0, 1 here. The reason why the partials are undefined is because you've got this cusp happening here. Yeah, it's like that sharp corner, and it turns out to be a relative max as well as an absolute max. So this critical point gives us a rel max, which is also an absolute max. The max of the Hershey Kiss. Fine. Last but not least, for our prep problems, just the cheesy problem, here is a surface given by fxy, y squared minus x squared. Well, what, if any, are the critical points? So I go, all right, what are the partials? The fx is negative 2x, fy is 2y, and I'm going to simultaneously set these partials equal to 0. So then what? Well, I once again get the point 0, 0 is a critical point. So is this going to be a max or a min or what? And it turns out that this surface here, if I graph it, let me just try to, well, let's get another page because I ran out of room. When I graph it, it's kind of an interesting looking surface because it's one of those hyperboloids. And so what I like to do is, I'll show you what I mean here. Oh boy. The surface kind of looks like this. And the point right there is what we call a saddle point. And the reason why is if I put this surface on a horse, and I'm going to try to draw a horse right now. The horse is not part of the surface, okay? He's just going to have this saddle on him. I'm trying to be ridiculous here. Woo! We used to draw horses when we were kids growing up because my girlfriend was really into horseback riding. Okay, so I hope you can see that this, this surface, this hyperboloid, is like a saddle fitting on a horse, okay? And we call this a saddle point, and it's not a max or a min. So here's what I want you to imagine. If I pet my horse going in this direction, that saddle point kind of looks like a minimum of the saddle. But if I pet my horse around his girth like this, along this direction, that saddle point kind of looks like a max, but it's neither. It's neither a max or a min. It's called a saddle point. Cool beans, huh? So those are the three options that you have. So we're not getting a max or a min. This critical point is giving us a saddle point, neither a max or a min. And so we don't have inflection points here in Calc 3. We have something called a saddle point. All right, now for the big theorem. And then I'm going to do a problem, and then I'd like you to try one. So that's my whole thing here. So this second partials test theorem, which is also called the D test. I'll get into that in a moment why. I'm going to usually call it the D test. But we'll see why it's called the D test. This is similar to the second derivative test that you had in Calc 1. So let me just quickly review what the second derivative test is. When you had a rel max in Calc 2, and you first found a critical point, so you found that f prime of c was 0, okay? When you evaluated your critical point at the second derivative and you got a negative number, that meant that the graph was concave down. Do you remember this? And when your graph was concave down, you ended up with a rel max. That's when your second derivative was negative. On the other hand, if you had a critical point at C that you already found because your first derivative was 0, and you evaluated that critical point at the second derivative and it was positive, that meant the graph was concave up, and that meant you had a rel min. Does this ring a bell for any of you folks? Yes, no, maybe?
It's very familiar.
Sort of, kind of. Well, this second partials test is analogous to that second derivative test that you did in Calc 1. So watch how it is. So first you got to get your critical points. Okay, so first get your critical points. That's step 1. If you don't have any critical points in hand, forget even applying this second partials test because it won't work. Okay, so what you're going to do before you do anything is you got to create this quantity known as the D quantity, and you have to go get some second partials. You're going to take fxx, multiply it by fyy, and subtract fxy getting squared, and you evaluate your critical point, or if you've more than one critical point, you have to evaluate more than once for this D quantity, okay? So here's what it says. If D ends up being greater than 0 when you plug in your critical point, and your fxx is positive at that critical point, so both are positive, that's kind of like having concave up, but oh boy, that didn't go so well. That's kind of like having concave up for your second derivative test. So that means you have a relative minimum. Now notice these are both positive, And both positive means relative minimum. Sometimes our brains, being human, we like to think of, oh, everything's positive. That means a max, right? Nuh-uh, it's the opposite. Don't blow this, because on a test or a quiz, you get this backwards. I can't give you any partial credit because it means you're not getting it. So don't make a silly mistake like that. On the other hand, if D is positive, but your fxx is negative when you evaluate it at the critical point, that's analogous to being concave down, then you have a rel max. Now, if your D is negative, you don't even have to bother checking the fxx. You can immediately conclude you got the saddle point going there. And finally, if D is equal to 0, your test is inconclusive. And that happened here in Calc 1, because in Calc 1, when you evaluated your second derivative at the critical point and you got 0, that second derivative test was inconclusive and you had to go do something else. Probably the test for increasing, decreasing functions. We don't have that, but you can do something similar by plugging in points around it. Okay, so I'm going to do a problem and then you're going to do one. So watch closely because, you know, it gets a little dicey here. We're going to have to solve a system of nonlinear equations. It's going to be kind of tough. Okay, so here is some function. It's good, you know, represents a surface in space. Go get the extrema and saddle points, if any. Fine. All right, so I'm going to go get fx, and I get 2x plus 1 minus 3y. Go get fy. I get 3y squared minus 3x. Simultaneously set those partials equal to 0 because you're trying to find critical points. So I set these both equal to 0, and I want you to notice that I get a non-linear system of equations. It's non-linear because of this 3y squared term. If that 3y squared term had been 3y only, it would have been a linear system of equations. But it's not. It's nonlinear. Now, when you're dealing with a nonlinear system of equations, the best way to deal with it is to use the method of substitution, where you solve one of the equations for a variable, preferably the easiest one, and you substitute that into the other equation and thereby have an equation with a single variable, solve for that one variable, and then plug it back into either of the originals to get the other variable. Okay? Substitution method. Now, which of these equations looks the easiest to solve for a variable? Be careful, because the first equation is not the best choice, because you'll end up with fractions. Ugh, it's going to be a mess. It's not wrong. It'll still work out for you, but you'll have a lot more pain. And if you like pain, knock yourself out. I personally try to avoid as much pain as possible when I'm trying to solve a nonlinear system. So I'm going to solve the second equation for x because I claim it's actually kind of easy. If I add 3x to both sides and then divide both sides by 3, I get x equals y squared. And so I'm going to substitute that into the first partial for x. So the first partial was 2x plus 1 minus 3y equals 0. And if I substitute x equals y squared in there, that's why they call it the substitution method, I now have an equation in y. And folks, this is a quadratic equation. Please solve it using your algebra knowledge. Don't do weird things to solve quadratics. I have people like, oh, I'll get 1 on one side and then, oh, I don't even want to get into it. Now, you could use the quadratic formula. That always works, but that's also a little dangerous because if you mess up with one negative, the whole thing is messed up. I claim this factors, so I'm going to factor and apply the zero product property. The key number is 2 times 1, which is 2, and the factors of positive 2 that add to negative 3 are negative 2 and negative 1. And I use negative 2 and negative 1 to split the middle term into 2 pieces. So negative 3y is equivalent to negative 2y plus negative 1y. I copy down the first and last terms, and then I factor by grouping. So the GCF of the first two terms is 2y, and so I'll factor that out, and the other factor is y minus 1. The other pair doesn't really have anything in common, but it's required to pull something out. You could pull out a 1, but I claim the smarter choice is to pull out a -1. Why is it the smartest choice?
Because it matches the first portion, so you can group it.
Yeah, because the other factor now is a match. You can factor out a y minus 1 because it's now a common factor. And now I factored the polynomial. That's a little bit of algebra for you. And now the ZPP, the zero product principle, says if something times something equals 0, it must be the case that one of those factors equals 0, or they both do. And so I individually set them equal to 0, and I get two answers. Which answer is correct? Both, but you're not done, because all you're saying now is you have two solutions to this nonlinear system of equations, and you have the y coordinates only for these two solutions. These are the two critical points. So what are the corresponding x coordinates? You could substitute these values of y back into either of these original equations, but I claim, hey, you already solved x in terms of y way over here. Why don't you use it? Sure. In other words, x is equal to y squared. So if y is 1, then the corresponding x coordinate is 1. And if y is a half, well, then the corresponding x coordinate is 1/4. And folks, these are the critical points. And I'll give you some partial credit if you at least give me the critical points. Yay. Now, are those maxes or mins? We don't know. You don't want to guess. And they might be neither. They may be a saddle point. So you have to do some more work. Well, what kind of work? You have to perform the d-test. So why do they call this the d-test? Because it's actually a determinant. What do I mean? Well, I claim that the determinant is a determinant of this matrix where the top row is fxx and fxy, and the bottom row is fyx, fyy. And so if you take the determinant, the D stands for determinant, you'll get fxx times fyy, and that's this guy right here, minus the product along the minor diagonal, fxy times fyx. Now, wait a minute, though. It doesn't look like they're doing that here. They're just doing fxy getting squared. But I claim it's the same thing. Why? Do you guys remember?
They both lead up with the same derivative.
Yeah, fxy and fyx, the mixed partials, are typically equal. So this D, this determinant of this matrix, is the same. So that's what it is. That's where the D, why they call it the D test. So if we get fxx and fyy and fxy, and then we'll use those to create our D quantity, I get fxx, the derivative of fx with respect to x is 2. The derivative of fy with respect to y is 6y. And the derivative of fx with respect to y is -3. So the D is going to be the fxx, 2, times fyy, 6y, minus fxy getting squared. So if I write it a little bit nicer, it looks like D is 12y minus 9. So what we have to do is we have to evaluate D at each of the critical points and then use the theorem to figure out if we've got a max or a min or a saddle point. So I'll use the first critical point, 1, 1. And I get 12 times 1 minus 9, which is 3. But that's a number greater than 0. Ooh. Ooh. What does the D test tell us if D is greater than 0?
It's a relative min.
Nope, we don't know. Why not? Because both number 1 and number 2 have d greater than 0. You have to do one more thing if your d is greater than 0. You have to evaluate fxx at your critical point. And then you can make the determination of if you have a relative min or a relative max. Okay. So what is fxx evaluated at this point, 1, 1? Well, fxx for this particular case is a constant. It's always 2 regardless. Okay. And 2, of course, is a number that's greater than 0. Okay. So we have both d and fxx positive. So what does the d-test theorem tell us if both are positive?
Max.
You have not a max.
Midpoint.
Remember, I told you it's backwards. You've got a min. A min. Don't blow this, people, because I'm just going to take away so many points. That's not going to be pretty. So we have a relative min at the point 1, 1. Now, a lot of times they're going to ask you for that minimum value. So the actual minimum value at the point 1, 1 is the function evaluated at 1, 1. Which is kind of a pain for us because it's y cubed plus x squared plus x minus 3 times xy minus 5. And so that actual min value is, I get negative 5. But we're not done because now we have to test the other point, 1/4 a half. And then I guess I'll finish it there. We don't have time for you to work on something. We'll start next week with that. So d evaluated at the point 1/4 1/2 is 12y, 12 times a half, minus 9. But that's 6 minus 9, which is negative 3. Oh, but negative 3 is a number less than 0. What does the theorem, the d-test theorem, also known as the second partial test theorem, tell us what's going on if d is less than 0?
Saddle point.
Saddle point. Yeah. Yeah, we got a saddle point at 1/4 a half. Now, if they asked you for the value of your function at the saddle point, you could evaluate, but it's not going to give you a min or a max, and I get a really weird number, negative 79/16. So, okay, fine. But we have a saddle point, which is neither a max or a min, as you saw with my little horse picture. And we're done with this problem. Yay. So let's recap. When you're being asked to find relative extrema and saddle points, if any, for some function of 2 variables, you're going to go through this whole process. You're going to first get your first partials, simultaneously set them equal to 0, and you get a system of equations. If you're lucky, it's a linear system. If you're not as lucky, you'll have a nonlinear, but just use the method of substitution and just get your solution or solutions. And here we got 2 solutions. And folks, when you solve a nonlinear system, you can get 1 solution, 2 solutions, or even more. So you can get, like, heck, infinity solutions. That's a possibility. But I don't have time to test all infinity answers. Yeah, well, okay. Once you get your critical points, the solutions for your nonlinear system here, you got to test them by forming the d quantity and evaluating d at your critical point or points. And then you use the theorem to tell you if you've got the max or the min or a saddle point. So we found we had a min and a saddle point, and that's it. And I'm done. Any questions on that?
That's so far.